Buon pomeriggio a tutti e benvenuti alla presentazione finale di Webvalley 2021. Siamo arrivati anche quest'anno a questa giornata, è stata una grande e lunga avventura. Anche quest'anno, come l'anno scorso, siamo stati costretti, direi, a lavorare in una modalità, diciamo, ibrida, quindi abbiamo fatto una regia qui in Artigianelli, che ci ha ospitato anche quest'anno come tutor, e ci siamo collegati ai ragazzi in modo virtuale, quindi abbiamo lavorato. Abbiamo avuto una squadra di 17 ragazzi, abbiamo avuto 12 italiani e 5 stranieri, Stati Uniti, Brasile e Russia, quindi abbiamo dovuto gestire anche una diversità, diciamo, di fuso orario multiplo, quindi la sperimentiamo anche oggi in questa presentazione finale. Un po' come l'anno scorso chiedo un po' di pazienza se avremo qualche problema, ma mi auguro di no. Abbiamo fatto abbastanza prove, quindi siamo ben contenti di essere qui, di presentarvi il lavoro che hanno fatto. Il team è stato molto professionale, hanno lavorato benissimo, quindi faccio i complimenti a loro, alle loro scuole. È stato davvero molto bello lavorare insieme quest'anno. E ringrazio tutta la squadra dei tutor, è tutta intorno a me, siamo un po' a distanza, quindi non siamo qui tutti insieme, però è stato davvero un ottimo team e grazie anche ai docenti artigianelli che ci hanno accompagnato nella metodologia, diciamo, del progetto, quindi hanno accompagnato il progetto e una studentessa che con noi 2 settimane ha fatto da communication officer e quindi ha seguito anche tutta la parte, diciamo, grafica del progetto, che potrete vedere anche dal lavoro dei ragazzi, insomma è stato davvero efficace. Io non vi rubo più altri minuti, lascio la parola a Giuseppe Jurman, il secondo direttore della scuola, e con cui, insomma, ormai sono un po' di anni che lavoriamo insieme e dal 2011 siamo in lingua inglese e quindi anche quest'anno la presentazione dei ragazzi è in lingua inglese. Grazie mille.
Thanks, Claudia. Welcome everybody from our headquarters here in the Studio Artigianelli. And we're ready to start our final presentation, our final event for Webvalley 2021. Okay. We will present you a very interesting project also this year. This year we are dealing with an application of AI in healthcare. And as Claudia said before in Italian, the boys and girls were a wonderful team. They were very professional and they worked very hard and produced quite a few interesting things. And they are ready to present to you. So I won't take the scene anymore. So I let the guys from the Webvalley 2021 team to start the official presentation for this Webvalley event. Okay, thanks a lot, and let's go.
Good afternoon, everyone, and thanks for being here. Let us first introduce ourselves. We are the Webvalley 2021 team, a research group of 17 junior researchers in data science for precision medicine. Today, the project is a collaborative effort supported by FBK researchers together with Dr. Inchiostro from APSS and Dr. Monica Motz from Dedalus Life Science, with computing support provided by Microsoft. We will follow the structure of a scientific paper, ready to be submitted to a scientific journal. Okay, I'm going to start again. Okay, I'm going to start again. I hope that you can hear me. So good afternoon, everyone. Thank you for being here. Let us introduce ourselves. So this is our team. We are the Webvalley 2021 team, a research group of 17 junior researchers in data science for precision medicine. Today, we present our project, Predicting Comorbidities in Type 2 Diabetic Patients, a data science approach which is tackling the challenge of predicting the onset of comorbidities of diabetic patients from a large cohort provided by GPI. The project is a collaborative effort supported by FBK researchers, together with Dr. Inchiostro from APSS and Dr. Monica Moz from Daedalus Life Science, with computing support provided by Microsoft. We will follow the structure of a scientific paper ready to be submitted to a scientific journal. Therefore, we start with the introduction, providing the essential notions about diabetes and its complications and explicitly starting our task. As a first step, we need to properly set our work into the relevant scientific environment, outlining the state of the art of the related works published in the literature. Then we describe the structure of the data, including the required pre-processing to get data ready for modeling. Furthermore, we state the privacy approaches we were required to adopt to correctly handle such sensible data. And next comes the description of all the methods and algorithms we employed for the analysis. In particular, we first discuss tools from data exploration, data visualization, dimensionality reduction, and unsupervised learning. Then we describe the predictive modeling strategies we adopted, also including details about training and validation in the supervised learning setup. We then move to the presentation of the results we had obtained and to the discussion of our findings. Finally, we conclude with a few considerations about the significance of the work and the potential future developments. So let's start.
The aim of the project is to create a tool to predict diabetes comorbidities by using artificial intelligence. In fact, being able to predict comorbidities can ensure a more appropriate and targeted treatment, which facilitates patients' adherence to care and may also intercept and correct the trajectory leading to complication. So it can basically limit the impact of complication on patients' life. Diabetes mellitus is a group of metabolic diseases that is characterized by a condition called hyperglycemia, so high glucose concentration in blood, that results from a deficit in insulin secretion and/or in insulin action. Hyperglycemia is affected by insulin sensitivity, which can change based on the type of diabetes, time of the day, for example, before or after meals, level of activity, and daily hormone secretion. If hyperglycemia becomes chronic, it can lead to a group of comorbidities that is an additional condition to the main one that can be subdivided into macrovascular and microvascular. There are two different types of diabetes, type 1, more spread among children, and type 2 diabetes. In our study, we focused on type 2 diabetes for several reasons. These are the most relevant. More people are affected by type 2 diabetes than type 1, so 6.3% of the population is affected by type 2 diabetes, while 0.15% of individuals by type 1. Furthermore, type 2 diabetes presents several complications, such as retinopathy or ischemic stroke, which we are briefly going to analyze. And finally, it has been shown that early intervention reduces the subsequent risk of developing these comorbidities. Type 2 diabetes is a very common disease, which is doomed to increase in the future. In particular, currently, 6.3% of the population is affected by diabetes, for a total of 400 million patients all around the world. Furthermore, as shown in the plot, diabetes increases the probability of developing various complications and, as a consequence, mortality. Individuals with diabetes are more likely to die from ischemic heart disease or from kidney disease compared to individuals who aren't affected by it.
A According to statistics, 1 in 11 adults between 20 and 79 years old have diabetes. That is 463 million people. 1 in 2 people with diabetes are undiagnosed. That is 232 million people. 10% of global health expenditure is spent on diabetes, and that is 760 billion US dollars. 79% of people with diabetes live in low and middle income countries. Over 1.1 million children and teens below 20 years old have type 1 diabetes. 1 in 13 adults between 20 and 79 years old have impaired glucose tolerance, and that is 274 million people. The situations of countries like the USA, China, and India is particularly alarming, as shown in the following plot. Type 2 diabetes comorbidities are divided into two groups, acute and chronic. In this project, we concentrate especially on the second group. Chronic complications are caused by the prolonged years of hyperglycemia, which in turn provokes more cardiovascular risks, both micro and macrovascular. Microvascular comorbidities are a group of long-term complications that affect small blood vessels. In particular, we can find retinopathy, an illness of the eyes that begins as non-proliferative and progresses as proliferative. It can damage the eyes, resulting in blindness. Then there's nephropathy, an illness of the kidneys characterized by persistent proteinuria. It can result in kidney failure and end-stage renal failure. Neuropathy, a heterogeneous conditions classified by the damage and dysfunctions of one or more peripheral nerves. Among these complications, retinopathy is the easiest to diagnose and predict from a clinical visit, having the highest prevalence, while the other two are more of an unknown. Macrovascular comorbidities include myocardial infarction, which is an occlusion of the coronary artery with the death of the myocardial tissue. Then there is ischemic stroke, which is an occlusion of the cerebral artery with the death of the brain tissue. Then there's peripheral vascular disease, namely cerebral stenosis or occlusion of the leg arteries with ischemic damage of the leg tissue. And lastly, there's heart failure, which leads to an insufficient function of the heart, incapacity to carry out normal daily activities due to the lack of strength, and breathlessness until acute respiratory failure or sudden death. In addition, the previous mentioned complications are highly influenced by the so-called risk factors. This means that the odds of developing comorbidity are bound with exposure time to every single risk factor, level of risk factor, their interplay among risk factors, and susceptibility of the single patients to every single factor. Examples of the risk factors are age, the older you are, the bigger risk you have, sex, if you are male, you have bigger risks, date of the diagnosis, the longer time has passed, the more risk you have, obesity, if present, the risk is greater, and then family history. The more relatives with diabetes, the greater the risks.
A collaboration with a diabetic patient named Cecilia Scainelli offered us further notions and details about this illness, its impact on the patient's daily life, and its possible complications. Cecilia's report has also been a perfect driver to understand and find out possible future developments of our project. Some parts of the testimony impacted us for the progress of the project, like this one. I've programmed an algorithm which calculates my need for insulin based on my glucose level. I came up with this idea and I decided to develop it. To prevent the side effects of diabetes, patients can work mainly on three factors: food and calories management, since depending on the amount and type of waste, the insulin level in blood can be influenced; sport activity, which can act as a leverage for glucose level; and treatment improvement, which is the aspect our project is focusing on. Concerning therapies, diabetic patients have, for example, to deal with insulin measurements and injections. Technology in this field has improved a lot over time, making them less invasive and automated. In the past, patients had to continuously measure their level of glucose and needed between 6 to 8 injections per day. This changed, for example, with the invention of the insulin pump, which takes a measurement every 5 minutes and then injects the right amount of insulin. Also, our project intends to contribute to treatment improvement since comorbidities prediction can help medical doctors in designing personalized treatments for diabetes patients. In order to outline the state of the art of the related work published in the literature, we explored several scientific sources. In particular, we focused on three following references due to their novelty and significance for the task we are facing. The importance of domain knowledge, nationwide prediction of type 2 diabetes, and machine learning methods to predict diabetes complication. The first article is about the importance of domain knowledge in data research science, showing how domain knowledge informs every stage of the data analysis workflow, starting from the problem formulation, passing to data collection, data preprocessing, modeling, and going to the final part of the project, that is, result interpretation. The second one reports a research project carried out by a group of Danish researchers from the University of Copenhagen, whose goal was to predict the future onset of several complications connected with diabetes within the 5-year window from the first type 2 diabetes diagnosis. The third article is called Machine Learning Methods to Predict Diabetes Complications, and it is the scientific paper of a project with the same goal as ours, that was addressed using machine learning and data science.
Now that we set the scientific background and the research goal of our project, we'll proceed talking about the data. As already mentioned, in our project we work on a large, anonymized dataset provided by GPI, a leading Italian firm that supplies healthcare solutions. The dataset is a CSV file that can be represented as a table, which contains one row per medical appointment. In this dataset, we can identify 3 categories of data: demographic data, that are the general data about the patient, such as gender and age; laboratory data, that are represented by the blood test results; and comorbidities data, concerning diabetes-related complications affecting the patient, that are represented by Boolean values. This represents our target variable. This dataset has been gathered during 8 years between 2012 and 2019, and it stores national longitudinal health register data of Italian patients. It's a really big dataset composed of 7,187 records of 6,741 patients. Each patient has multiple records because there are more appointments registered in the dataset. 46 patient variables for each record, including anonymized IDs. We decided to store the dataset on a virtual machine that FBK provided us with in order to keep it in a safe space, avoiding the risk of accidentally exposing it. As far as privacy is concerned, the most sensitive data has already been pseudonymized, but we'll discuss the handling of privacy in more detail later.
In data exploration, the first step is to get a general understanding of the data. Here on the left, we can see a histogram plotted for each numerical variable. A histogram essentially represents the frequency distribution of a single continuous numerical variable, and hence, we can get an understanding of the distribution of all the numerical variables. We can immediately notice that some of the variables are asymmetric, like creatinine, neutroph, and triglycerides. Instead, others are uniformly distributed and symmetric, like hemoglobin, hematocrit, and erythrocytes. Additionally, all histograms are unimodal. As such, we can see that the symmetric numerical variables follow a relatively normal distribution. This, in turn, represents that the numerical variables are relatively unbiased. The graph on the right shows the ratio of the patients with and without a specific comorbidity. We can immediately notice the large imbalance in the class distribution of the data of whether a patient has a comorbidity or not. This is one of the factors we must consider so that the model is not biased towards one class, and we will see how the model training team overcame.
Since we're using people's personal data, it's very important to have them pseudonymized in order to avoid giving third parties the opportunity to identify the subject the data are referring to. Pseudonymization is a de-identification procedure by which personally identifiable information fields within a data record are replaced by one or more artificial identifiers or pseudonyms. As already mentioned, the most sensitive data in our dataset had previously been pseudonymized. First, they pseudonymized patients' demographic data that would not influence the analytic process. In particular, they pseudonymized the following fields: name and surname, substituting by the numerical ID, birth date, substituted by the age. These are the most important data to preserve for the sake of the patient's right to not have their records exposed. We also decided to pseudonymize the appointment dates to add one more privacy layer. We did that in order to make the cross-referencing process harder in case someone tried to gather information. Since privacy is really important, the European Union decided to create the GDPR, that is the General Data Protection Regulation, and it's been followed since 2016. Its goal is to enhance individuals' control and rights over the personal data. One of its fundamental points is the privacy by design. This section of the GDPR requires companies to design their systems endowed with the proper security protocols in place from the start. And that's why we started working on the privacy task as soon as we got the data file, working just on the pseudonymized dataset.
Let's pass to the methods we adopted in our project. Data processing manipulates the data in order to enhance the performance of the machine learning model. In the first step of the processing pipeline, we aggregate the various clinical visits of each patient. This way, the dimensionality of the dataset is reduced from more than 16,000 to almost 7,000 entries. In the second, we remove redundant variables. For example, lymphocytes are represented both in percentage and by absolute values. For these situations, we choose to keep the absolute values. Of the 15 different comorbidities contained in the dataset, we focus on the most prevalent 5. Those involve eye, thyroid, strokes, hypertension, and kidney. In particular, we are interested in estimating the risk of developing any of these comorbidities in the future. Therefore, we created a target variable that indicates the presence of any of them. The last pre-processing step converts categorical variable into numerical values.
Before training our models, we pre-process our dataset. The first pre-processing step scales all the input variables into the same range of values. This step facilitates the learning process of the models and reduces possible numerical errors. However, the dataset we're using is not balanced because of the two categories. One is significantly larger than the other one. Hence, in order to obtain a better learning training set for the AI algorithm, we decide to generate synthetic data. To generate this data, we use the SMOTE, or synthetic minority oversampling technique. As it can be seen in these images, the SMOTE generates new data points, laying them on the imaginary lines, then interconnect the real data.
Correlation is a statistical tool that allows us to understand how much two variables are linearly related. It is used to summarize and see patterns in big amounts of data, and normally it can be significantly used in predictions, but it doesn't necessarily imply causation. In our case, the formula used to calculate the correlation coefficient was Pearson correlation, the most widely used, and that you can see at the bottom of this slide.
As Filippo said, one of the first steps in a data science project is to start by exploring the data itself. Nowadays, real-world data that is collected comes with many variables, which makes it virtually impossible to visualize data and train models. Therefore, it is valuable to understand high-dimensional datasets with various dimensionality reduction techniques. The first technique that we tried was PCA, which reduces the dimensions of the data while still retaining most of the important information. PCA works by calculating the eigenvectors that point of the variance of the data using matrices, called components. The result highlights the features that represent the largest amounts of the variance of the dataset.
In our pipeline, we wanted to optimize our methods of analysis, so we explored another dimensionality reduction technique called uniform manifold approximation and projection, also known as UMAP. UMAP is used to transform the data to a lower dimensional space called an embedding while preserving the general topological structure. Because our data was high dimensional, we had to reduce it to an embedding that could be plotted and then clustered. After UMAP, we used multiple clustering algorithms ranging from hierarchical, density-based, model-based, centroid-based, and graph-based. Clustering is a type of unsupervised learning that finds distinct partitions within the embedding by seeking for groups with similar data points. The difference between the types of clustering is found within the metrics for what is considered similar. Some may use distance while others use variance. In our project, clustering is used to find similar patients and/or comorbidities within the dataset. There are many different clustering techniques that work in various ways. In our project, we compared many of them.
After the data exploration comes the model training step, which is aimed at searching the best combination of parameters and algorithms to create a machine learning model to predict the outcome of unseen data. In particular, since we adopt AI solutions, our code is not designed to tackle a deterministic problem, but is aimed to enable the machine to learn how to solve problems without being explicitly programmed to a specific task, but rather to extract insight from data patterns.
In order to achieve a better performance, we try 4 different kinds of AI algorithms. The first algorithm we use is the SVM model, a linear and nonlinear model for classification and regression problems. In order to make the prediction, this algorithm creates a hyperplane which divides the data into 2 or more categories, as this can be seen in the image. The second algorithm we use is the random forest, a type of decision tree method. Random forest is a machine learning algorithm that relies on ensemble learning. This technique combines many simple classifiers to achieve solutions to complex problems. The third kind of model we use is the k-nearest neighbor, or KNN. This method, by relying on the given number of labels k, assumes that similar data points are close to each other, dividing into categories the overall dataset. Last, we used an artificial neural network. This algorithm is an attempt to simulate the functioning of the neurons of the human brain. Using this approach, our algorithm is able to model prediction problems and recognize complex patterns. After completing the model training, we save and give all of them to the model validation team.
So, model validation is the set of processes and activities intended to quantify the performance that could be expected from a given machine learning model on unseen data. Models can be validated by comparing the predictions made by the algorithm over a set of new data with the correct results. The model validation process supports the model and the reliability of its outputs, and its purpose is about testing the plausibility of the performance it has. So, some theoretical notes that will be useful to understand the graphs later. The bias is a phenomenon that occurs when the algorithms produce results that are systematically prejudiced. due to erroneous assumptions in the machine learning process. And variance instead is a type of error that occurs due to a model sensitivity to small fluctuation in the training set. Underfitting occurs when the model is unable to capture the underlying patterns of the data. These models usually have a low variance and a high bias, so are usually simple ones which are unable to capture the complex patterns in the data. Overfitting occurs instead when the model captures the noise and the outliers in the data along with the underlying pattern. These models are usually have high variance and low bias. If the models are complex, they will be prone to overfitting.
An AI model becomes useful only if this is properly trained on a well-built dataset, and the only way to discover that is to analyze its performance under different scenarios, taking into account as many variables as possible. For a model to be considered useful, it's crucial that it has a good performance on previously unseen data, submitted to the model in the validation process. To validate models, data is being split into several different sets: training, validation, and test. Training and validation sets are used to build and select the best performing parameters. The test set is then used to ensure the quality of the model and its true performances. Following this experimental design is extremely important, especially for biomedical applications, on which automated decisions may have a heavy effect on people's life. From this real-life data from a biomedical context, we need to make sure our algorithms can provide the reliability and validity of the data. Reliability is the extent to which the results can be reproduced when the research is repeated under the same conditions, and validity is the extent to which the results really measure what they are supposed to measure. Reliable data is not always valid, and that's when we need to assure that data is both reliable and valid.
To perform the validation, we tried a variety of different metrics. A lot of them were based on the confusion metrics. Could you please? Okay. The confusion metrics used to visualize the classification accuracy of a machine learning model. In the table, each row represents the value predicted by the model, while each column contains the actual values that should have been predicted. Since our model needs to only predict whether a patient will develop or not a specific or any complication, we'll only have a positive or negative outcome for each prediction. Due to that, our confusion matrix will end up looking like the one in the picture. We have 2 rows and 2 columns, which forms 4 different cells that can be labeled with 4 different names. The true positive cell, or TP, which contains all the positive samples that have been correctly identified by the model. The false positive cell, or FP, which contains all the negative samples that have been incorrectly labeled by the model as positive. The false negative cell, or FN, which contains all the positive samples that have been incorrectly labeled by the model as negative, and the true negative sample, and the true negative cell, which contains all the negative samples that have been correctly identified by the model. From this table, it's then possible to calculate various different metrics, such as sensitivity, specificity, and accuracy. But all those metrics share a common problem. They do not consider every value of the confusion matrix. And this leads to validation error, especially if the positive and negative class are unbalanced. To solve this problem, we ended up using a different metric, the Matthew correlation coefficient. The MCC is calculated with the formula you see on screen, and it's a value that ranges from -1 to 1, where 1 corresponds to a perfect prediction, 0 corresponds to a random classification, and -1 corresponds to a perfectly wrong classification. As you can see, the MCC formula contains all the confusion matrix values. This allows us to get a correct estimation even with an unbalanced dataset. In fact, the MCC is actually the best known method to evaluate machine learning models. In addition to the MCC, we also used 2 different metrics. The precision recall curve, which is a curve that shows the trade-off between precision and recall for different thresholds. A high area under the curve represents both high recall and high precision, where high precision relates to a low false positive rate, and high recall relates to a low false negative rate, and the ROCQ, which is a graphical scheme for binary classifiers. Along the two axes are represented respectively the true positive rate and the false positive rate. In other words, the ROCQ studies the relationship between true and false alarms.
Cross-validation is a model validation technique for assessing how the results of a statistical analysis will generate to an independent dataset. In a prediction problem, a model is used given a dataset of known data, training dataset, and a dataset of unknown data, teaching dataset. The goal of cross-validation is to test the model's ability to predict new data that wasn't used to estimating it. One round of cross-validation involves parenting a sample of data intra-complementary subset, performing the analysis of one subset called the training subset, and validation, the analysis on the other subset called a validation set or testing set. In most methods, multiple rounds of cross-validation are performed using different partitions, and the validation results are combined like averaged. In summary, cross-validation combines measure of fitness in predict to derive a more accurate estimate of model prediction performance.
As you can imagine, for model training and also for the model validation, we need some tools. Let's start with Visual Studio Code and Jupyter, respectively our editor, the place where we code. And next we have Jupyter, an interactive coding platform, very helpful for expressive programming. Python is the language code we used with some libraries, NumPy and Pandas, to manage the dataset, and sklearn to help us to train our AI model in a easier way. Least, but not least, in the virtual machines that are as our computers, but online. In this way, we can scale in a better way the performances, and in case of crash, we are not affected of the consequences. And it happened. And this is the Azure Cloud console, where the tutors checked if we work properly. And as you can see, we used a lot of virtual machine. Now that we have understood the entire process of our project, we will proceed talking about the results.
The first result we had were from correlation. We initially plotted a correlation matrix to try to find factors correlated to the comorbidities, but since the starting dataset had almost 50 features, it was difficult to actually spot correlations in such a complex graph. Hence, as you can see on the left, we calculated the numerical correlation for each comorbidity, and we found out that 3 comorbidities are correlated to the other laboratory and demographic variables. So we plotted a correlation matrix using only the significant values, which you can see on the right. A correlation matrix is basically a square with the same variables shown in rows and columns. In the yellow circles, we can see the 3 correlations we were talking about. Females are correlated to thyroid disorders by 44%. Males are correlated to ischemic heart diseases by 13%. And the creatinine value in blood is correlated to main kidney complication by 11%. To verify that our dataset didn't have anomalies and that these correlations were reasonable, we checked the previous literature about these correlations, and we found these 3 scientific papers. The first study on the left takes in consideration a set of 117 patients affected by nephritis, confirms the fact that high levels of serum creatinine are an important risk factor for kidney complication. The second paper states that diabetic patients are normally 2 or 3 times more likely to be affected by diabetes than non-diabetic patients. And it also says that this value raises with the presence of certain demographic characteristics, such as female gender. While this final study on the right, which analyzed over 30 Brazilian patients from 1980 until 2005, highlights how males in general were more affected by ischemic heart diseases.
After applying PCA, the algorithm gave interesting results. The first 2 components accounted for 32% of the explained variance. This meant to us that we could visually set the comorbidities apart with clustering algorithms. After plotting the training and testing data with PCA, it became apparent to us that PCA was not a sufficient algorithm to accomplish an observable separation between classes. So we looked into other clustering and reduction algorithms.
With UMAP, we reduced the features of the dataset from an n-dimensional space down to 2 dimensions and plotted the embedding here. Then, we used it for both the training and testing data. Each subgroup has patients who have similar comorbidities. After UMAP, we then ran 9 clustering algorithms over the data to examine the partitions of possible subgroups. There are many clustering algorithms that work in different ways, so we tried various methods. Ward, Birch, K-means, and Gaussian mixture model visually performed best. As you can see, these algorithms were able to identify the potential subgroups seen in the data. However, further investigation of each cluster would be needed to confirm this.
Okay, so it's time for the machine learning results. We need to always remember that a bad validation is not necessarily the sign of a wrong approach to it, but it depends mostly on the dataset and on the type of model training that was used on the precise dataset. Still, it could happen that numbers are way lower than expected, and this is the moment when you have to try different approaches. If the model has not gone through basic set validation tests, then it might be possible that the model is an overfitted model, which performed well on the development sample but fails on unseen data. In this first graph, we can see the different average MCC values coming from the cross-validation analysis for the comorbidities we have considered. The black bars represent 95% confidence intervals, and also the metrics are grouped by color. Each color represents the model we have used. Here you can see the best results come from the NAF comorbidity. The neural network and random forests are the algorithms that are performing better. Just remember that this is the cross-validation graph, so those results are the results coming from the training set. Here instead, we can see the graph of the MCC value of the test set. Also here, we can see that the best results come from the NAF comorbidity using the random forest algorithm. For this reason, we have decided to consider only this model for the next analysis. EYE and HYP have high variability and low performance, especially for EYE. It is therefore assumed that there are many patients in the dataset, but only one has the comorbidity. Comparing the validation metrics to the training ones, it's important to notice that the values are very similar, and therefore the model did not overfit. So now we are considering only one comorbidity. It's time to analyze the composition of the prediction results. Those are 2 confusion matrices, one normalized on the right and one non-normalized on the left. From those, we can discover that the number of true negatives represent the major part of the prediction, 1,145. Instead, the false positive are less, 158. False negatives and true positives represent the smallest part of the predictions. In this slide, we can actually see the precision recall curve and the ROC curve. The precision recall curves show the trade-off between precision and recall for different thresholds. High gear under the curve represents both high recall and high precision, where high precision relates to a low false positive rate, and high recall relates to a low false negative rate. In the caption, you can also see the AP, which summarizes a precision recall curve as the weighted mean of precision achieved at each threshold. On the right, there is the ROC curve that features true positive rate on the epsilon axis and false positive rate on the x-axis. Here, the higher, the better. This graph represents a pretty good example of an S classifier. the better it works, the higher the value of true positive rates we retrieve. So we are sorry, we had a technical problem, so the electricity went down at the head office. So we'll restart from the last slide. So in this slide, we can actually see the precision recall curve and the ROC curve. The precision recall curve show the trade-off between precision and recall for different thresholds. And high area under the curve represents both high recall and high precision, where high precision relates to a low false positive rate and high recall relates to a low false negative rate. In the caption, you can also see the AP, which summarizes a precision recall curve as the weighted mean of precision achieved at each threshold. On the right, there is the ROC curve that features true positive rate on the epsilon axis and false positive rate on the x-axis. Here, the higher, the better. This graph represents a pretty good example of a nice classifier. The better it works, the higher the value of true positive rate we retrieve.
Let's discuss our results. The top-ranked 5 variables used by the model are creatinine, gender, red blood cell distribution weight, hemoglobin, and total cholesterol. Apart from creatinine, none of the other values are usually employed to predict diabetes complication in clinical practice. Having found a relationship between comorbidity and the other 4 features is thus another result that confirms how much machine learning can support healthcare. As far as comorbidities are concerned, the model gives results concerning all of them, but it produced the best outcomes in predicting nephropathy.
On the contrary, the least promising results are in predicting retinopathy, where we would need a different kind of information that can be captured by blood tests. In this case, information from eye examination would help improve the model results, but unfortunately, this kind of information was not available. And as far as conclusions are concerned, the fact that these models can predict the risk of a complication already from the very first clinical visit could be very useful for clinicians as well as for the patients. And this is very important since currently there are no clinical methods that can predict the risk of complication accurately.
Due to the results, the present project can contribute directly to the United Nations Organization Sustainable Development Goals. The goal that the present study can support is the third one, which is named as Good Health and Well-Being, which aims to promote well-being and ensure a healthy life for everyone at all stages. This way, our work has importance for the whole society. As implementing the study, it is possible to improve treatment strategies by predicting the risk of patients developing diabetes-related comorbidities. As a future development for the project, it will be possible to further exploit AI machine learning techniques. Indeed, some apps and chatbots have been created to improve patients with motivational, psychological, and medical support. Moreover, the employment of artificial intelligence could help reach very important results. For instance, a group of parents whose children are affected by T1D have programmed a device which regulates the insulin delivery and it tracks the glucose level. Its name is Closed Loop System App and was true for children who was not able to understand their body and its situation. Furthermore, devices containing an alert system could be created to motivate patients to do physical activity. For example, it will be possible to monitor the cardiac traces of a diabetic patient during different physical activities, both aerobic and aerobic. So, who would like to be our first reviewer? And then we have the references. Thank you.
Siete in diretta.
You like guys?
So the presentation is over, and we're here for Q&A and any doubts.
We can start reading the comments, maybe.
Yeah, we have a number of comments. Okay, let me go back here. Yeah. Okay. There were a lot of compliments and comments from people who liked UMAP and clustering. But there are no questions. So I guess we can also say goodbye to everyone. Okay.
Ci si vede?
Yeah.
Ok. Thank you very much everyone. Io ringrazio tutti quanti, ringrazio i ragazzi che sono riusciti a venire qua per la presentazione finale e ringrazio davvero tutti quanti, Artigianelli che ci ha ospitato, tutti quelli che hanno lavorato. Non so che altro dire, insomma, come sempre è stata una super avventura, una bellissima scuola e loro quest'anno sono i protagonisti. Grazie. Adesso facciamo la carrellata, dai. Vai, bene.
Mettiti la mascherina.
Bravissimi.
Grazie.
Ciao, grazie.
Okay, we can end the broadcast.